Hey there, today we're going over normal distribution word problems. First, I'm going to give a brief introduction to the normal probability distribution. Then we'll go over 4 basic types of normal curve calculations. We'll also talk about converting from a non-standard normal distribution to a standard normal distribution. Finally, we'll go over a typical normal distribution word problem and use the TI-84 calculator to get probabilities and cutoff scores. I added timestamps to this video, so feel free to navigate to the portion of the video you're interested in. So let's first talk about the normal probability distribution. We'll start by graphing the normal curve, and the first thing to notice is that it has the familiar bell shape that you've seen before when you learned about the empirical rule. You'll also notice that it is symmetric, and the mean, which we denote with the parameter mu, is located at the axis of symmetry, and is the x value at the center of the distribution that corresponds to the highest point on the curve. The normal curve you see here is the graph of a function called the normal probability density function. As you can see, it looks quite intimidating, but thankfully, you don't have to work with this function directly because you can use technology or tables to obtain probabilities. We'll talk more about this later. You can describe a normal distribution by its population mean and population standard deviation, and we use the following notation to mean that a continuous random variable x follows the normal distribution with parameters mu and sigma squared. Your professor may have mentioned examples of real-world phenomena that approximately follow the normal distribution, such as heights, IQ scores, and blood pressure. Each one of these examples will have an associated normal distribution with parameters mu and sigma. Another important property is that the total area under the curve is 1, and this is helpful when finding probabilities, especially if you use tables, which we'll talk about in the next video. Since we have symmetry about the mean and we know that the total area under the curve is 1, that means that the area under the half below or above the mean is 0.50. Now that we talked a bit about the normal probability distribution, let's go over the 4 basic types of normal curve calculations. The first case involves finding the area between 2 specified values, which we'll call a and b. So in other words, given a and b on the horizontal axis, how do we find the area under the curve bounded by these 2 values? That also raises another question. What do areas under the normal curve represent? The areas under the normal curve represent probabilities, so there's a correspondence between area and probability. For example, the probability that x lies between a and b is written as follows, and so the shaded region you see here represents that probability. Okay, so back to our original question. How do we find this probability or area under the curve? Well, one way is to use calculus, which requires evaluating an integral. However, calculus is not a prerequisite for elementary statistics, so instead we're going to use the TI-83 or 84 calculator to obtain probabilities. The command we're going to use is called normal CDF, and in general, this command requires a lower bound, an upper bound, the population mean, and the population standard deviation. We can access this command by pressing second, then vars to get to distribution, then selecting the second option, which is normal CDF. Since we're already here, the other command we'll be using in this video to find x scores or z scores is inverse norm, and we'll talk about this in a bit. The next type of normal curve calculation involves finding the area less than a specified value, or in other words, finding the probability that x is less than some value, let's call it a. So here we shade the area under the curve to the left of a, and we label this area using probability notation. Again, we use normal CDF to get the probability, but this time we specify a large negative number, such as negative E10, as a lower bound to represent negative infinity, the upper bound as a, and then the mean and the standard deviation. Some stats professors may use different numbers to represent infinity, such as 1000, 10,000, E99, and so forth. What matters here is that you use a large number. By the way, the reason why we're using large negative or positive numbers is because the normal distribution goes forever in both directions, where the density curve never touches the x-axis. The area under the curve or probability in these regions will be nearly 0 when we start to exceed 3 standard deviations away from the mean. The last case involves finding the area greater than a specified value, say b. So here we'll shade the area under the curve to the right of b, and we'll represent this area as the probability that x is greater than b. We'll again use the normal CDF command to find the probability. Here our lower bound will be b. For their upper bound, we'll use a large positive number like E10 and provide the mean and the standard deviation. One thing I want to point out is that the first 3 cases involved finding probabilities using normal CDF. For the next type of normal curve calculation, we're actually going to reverse the process. In other words, given an area or probability under the normal curve, how do we find a cutoff score? So in this situation, we're not interested in finding a probability because that's given to us. What we want is to find some x value on the horizontal axis that corresponds to the area or probability that is given to us. The calculator command we'll use for this situation is the inverse norm command. This command requires the area to the left of the cutoff score we're interested in finding, then the mean and the standard deviation. Again, the area you need to specify is the area to the left of the boundary line you see here. We'll take a look at an example shortly. It's also important to know that in some problems you'll be asked to find 2 cutoff scores, but the process will be the same. To summarize, these are the 4 basic normal curve calculations you will encounter when working on normal distribution word problems. 3 of these cases involve finding probabilities using normal CDF, and the last case involves finding a cutoff score using inverse norm. Feel free to reference this chart as you work on these types of problems. This chart shows the graphs along with the shaded regions as well as the probability notation and the TI-84 calculator commands. Now, just a quick note here. You probably noticed that I didn't use probabilities of the following form, but instead I used probabilities with the strict inequality symbols, like less than or greater than. And the reason is because for continuous random variables, the probability that x is equal to b is 0. This means that the probability that x is less than or equal to b is the same as the probability that x is less than b, and the same is true for the other case. Geometrically, what we're looking at is a vertical line at x equals b, and lines have no area, so that's the reason why the probability that x is equal to b is 0. When you're working with discrete random variables, like when you're calculating binomial probabilities, for example, that's a different story. The probability that x is less than or equal to b is not the same as the probability that x is less than b in that situation. Now, let's talk a bit about the standard normal distribution. The standard normal distribution is a normal distribution with the mean mu equals 0 and standard deviation sigma equals 1. We denote it using the following notation. The values on the horizontal axis represent z-scores. Recall that z-scores represent the number of standard deviations above or below the mean. Note that z-scores can be negative, positive, or 0. Z-scores positioned on the left half of the curve are always negative, and those on the right half are positive. For example, a z-score of 2 means 2 standard deviations above the mean. A z-score of -3 means 3 standard deviations below the mean. Now let's say we were interested in finding the area bounded by -2 and 2. We would write that the probability that z is between -2 and 2 is 0.954. So when we're working with a standard normal distribution, we use z instead of x. By the way, this probability should remind you of something. Recall from the empirical rule that about 95% of all values are within 2 standard deviations of the mean, and that's why our probability is 0.954. Also, you can find this probability using the normal CDF command I mentioned earlier. Just make sure that you use 0 for the mean and 1 for the standard deviation. Now, some of you have probably used tables to find normal probabilities, and these probabilities are based off of the standard normal distribution. So given a non-standard normal distribution, say a distribution with mean mu equals 100 and standard deviation sigma equals 15, we can use the conversion z equals x minus mu divided by sigma to standardize any normal distribution. In other words, once we perform this transformation, we can just go ahead and use tables to find the probability. In this example, the probability that x is between 85 and 115 is the same as the probability that z is between -1 and 1. So the areas are the same, and this is because all normal distributions have the same relationship between area and the number of standard deviations from the mean. Here, note that 85 and 115 are 1 standard deviation away from the mean, which is 100. For the graph on the right, we see that z equals -1 and z equals 1 are also 1 standard deviation away from the mean. Now, if you're in a stats class where you only need to use the TI-84 calculator to find normal probabilities, you don't really have to worry about this material because you can compute normal probabilities directly using the calculator. However, I know that there's some professors that will have their students first convert the x scores or x values to z scores and then use the calculator to do the rest. So the next thing I want to look at is the typical normal distribution word problem that you'll see in an elementary stats class. So I'm gonna go ahead and read the problem, and as I read the problem, I'll identify important keywords and write down the givens. Here it says that scores on the ACT test are normally distributed with a mean of 21.1 and a standard deviation of 4.8. We know right away that we're working with a normal distribution word problem because it states that ACT scores are normally distributed. I want to point that out because some students mix binomial probability word problems with normal distribution word problems, so you gotta make sure you read the problem carefully. We were also given that the population mean ACT score is 21.1, so we write mu equals 21.1, and that the population standard deviation is sigma equals 4.8. In this problem, our continuous random variable x is going to represent a randomly selected ACT score, and these are the values along the horizontal axis. There are 4 questions here. The first 3 involve finding a probability given some range of x values, which represent ACT scores. And the last question will involve finding a cutoff score, aka an x value, which represents an ACT score. We'll refer to the chart to answer these questions. Let's start with part A. Here they want us to find the probability that an ACT score is between 16 and 25. The keyword is between. Alright, so let's start by graphing a normal distribution centered at mu equals 21.1, and we'll also label the lower and upper bounds. Let's also draw the boundaries and shade the area under the curve between these 2 boundaries. We can represent the shaded area using probability notation. Now, looking at the chart, what calculator command do we use for this calculation? We use normal CDF, where the lower bound is 16, the upper bound is 25, and the last 2 parameters are the mean, which is 21.1, and the standard deviation, 4.8. I'm going to pull up the TI-84 calculator. Remember that to get to the normal CDF command, we press second, then press vars to get to distribution, then we select the second option, which is normal CDF. On the TI-84 calculator, you'll see this menu. Let's input the lower value, which is 16, then we type 25 for the upper value, then type the mean and standard deviation. Press enter and we get 0.648 rounded to 3 decimal places. As I mentioned earlier, some professors will ask you to first find the z-scores that correspond to the x values given in the problem, and then you use the calculator. If we do the problem using that approach, what we do is subtract the population mean 21.1 from each side of the inequality, and then we divide by 4.8. So the 16 gets converted to negative 1.06. The middle part is simply z, which is the conversion formula, and then the 25 gets converted to 0.81. In this case, when we use the normal CDF command, we specify negative 1.06 as a lower value, 0.81 as the upper value, and the mean is now 0 and standard deviation is 1. So be careful here because once we standardize the x scores, we now use the standard normal distribution, which has a mean of 0 and a standard deviation of 1. Okay, so let's type this information into the calculator. Press second, then go to vars, select the second option, then let's enter the information. You see that we get the exact same answer as before, which is 0.648. How do we interpret this result? Well, we can say that the proportion of ACT scores between 16 and 25 is 0.648. We can also say that 64.8% of the ACT scores are between 16 and 25. Of course, you can also say that the probability that a randomly selected ACT score is between 16 and 25 is 0.648. One thing I want to point out is that the terms probability, percent, and proportion can all be used in reference to the area under the curve. For example, another way that they may ask you this question is by saying something like, what percentage of ACT scores are between 16 and 25? Alright, let's look at part B. Here they want us to find the probability that an ACT score is greater than 20. Greater than 20, that's the keyword there. Let's draw the normal curve again and label it. We'll draw the boundary at 20. So, do we shade the left side or the right side? You guessed it, we shade the right side. Using probability notation, we write that p of x greater than 20. Now, what is the command that we use to find normal probabilities? Normal CDF. How do we get to it? We press second, then vars, and then select the second option. Now we type 20, a large positive number such as E10, then the mean and the standard deviation. Press enter and we get 0.591 rounded to 3 decimal places. Again, if your professor wants you to convert to the ACT scores to z-scores, go ahead and do that, and then use the calculator. I won't show you that step here since we already talked about it in part A, but you can verify that you did it correctly if you get the same answer I got here. For part C, we need to find the probability that an ACT score is less than 20, so less than 20, that's our keyword there. So let's draw the normal distribution, label it, and place a boundary at 20. In this case, we'll shade the area to the left. Using probability notation, we write p of x less than 20. And the calculator command, again, is normal CDF, so let's use our calculator. For the lower value, we'll use a large negative number like negative E10 to represent negative infinity. For the upper bound, we use 20, and then the usual 21.1 and 4.8. Press enter, and we get 0.409. Notice that this is a complement of part B, so in other words, if we subtract the answer in part B from 1, we get 0.409. For part D, they want us to find the ACT score that separates the top 20% from the bottom 80%. Another way of phrasing this question is by asking, what ACT score represents the 80th percentile? Now, this is different from parts A, B, and C, so let's take a look at it. As usual, we'll draw a normal curve and we'll shade an area of approximately 80%, so we'll just eyeball it. As I mentioned before, now we're doing the reverse process. So, given an area, we want to find an ACT score. Here we label the area to the left of the boundary line as 0.80, which means that the unshaded part is 0.20 because, again, the total area under the curve is 1. If we look at the chart, what calculator command do we use for this type of calculation? You guessed it, we use the inverse norm command. Remember that we get to the inverse norm command the same way we get to normal CDF by typing second, then vars, then select the third option. Okay, for the area, what do we use? Do we use 0.80 or 0.20? We use 0.80. Why? Because the calculator wants the area to the left of the cutoff score that we're looking for. So we type 0.80, then the mean and the standard deviation. Doing all that, we get 25.1. So 25.1 is the ACT score that separates the top 20% from the bottom 80%. Now, if your professor wants you to find the z-score first, you'll use inverse norm and type 0.80 as we did before, then the mean of 0 and a standard deviation of 1. So we get a z-score of 0.842, and then you substitute the z-score value into the formula x equals mu plus sigma times c, along with the mean and the standard deviation, and you should get the same answer as we did before. In summary, when you're working on these problems, make sure that you use the diagram by drawing the normal curve, clearly label the normal curve using the mean and the specified x values. Shade the area under the curve that represents the desired probability, and represent the area using probability notation, and write down the calculator command along with the values you provided to find the probability. If you follow these steps, you should be able to do any normal probability distribution problem. I hope this helps, and in the next video we'll look at how to find probabilities using tables. In the future, I'll go over problems where you have to use the central limit theorem, as well as calculating binomial probabilities using the normal distribution. Thanks for watching, and I'll see you next time.